Welcome to Spring LIB.
Okay, this is question 28.76, where we have this graph, figure 2876, that we're going to need to reference. And we have a solenoid that has two separate wires that we're winding around. And the wires are wound in the same direction. We have the same cylinder that they're being wound around. The length of the solenoid is 40 centimeters, so 0.4 meters. And we're told the diameter as well. And we're told that one of the currents in one of the wires is going to be fixed at 2 milliamps, which is 0.002 amps. And what we're trying to figure out is what are the number of windings in the first, in wire 1 and in wire 2. So this is the magnetic field if we had just a regular solenoid with only one wire. N is the number of windings, and I is the current in that one wire. When we have two, here I'm just going to, we can just take the sum, since the magnetic field they're just going to add. We'll have this expression for the first one, and then we'll have the number of windings on the second wire plus the current in the second wire. This is going to be the total net magnetic field from two wires that are wound around, creating a solenoid. So we can rewrite this just a little bit. We can pull out this factor of mu naught over L in both of these terms. Since those are both constants, this length isn't going to change. And then we have N1 times I1 plus N2 times I2. And so what we can do here, this is the axis, the y-axis in this figure that we're given gives us a hint that we're going to want to multiply by L over mu naught, which is going to bring this to the other side. So we'll get B times L divided by mu naught. And that's great because that's going to give us our y component on the axis here. And we have, remember, we're told what I1 is. So I'm just going to plug that in explicitly here. I1 is 2 milliamps, so 0.002 amps. So I'm just going to plug that in explicitly so that we can see this is an unknown variable because we don't know B. N1 we don't know, N2 we don't know, and I2 we also don't know. So now if we take a look at this graph that is plotted, basically what's going on is we're varying I2. So we're going to change the current in I2 and see what happens to this over here. Now, if we take a look at the form of this here, this is the equation for a regular line. If we have the form y equals m times x plus b, because n1 and n2 really are constants here. So here n2 is really going to be the slope. That's going to be the equivalent of this m. X is the variable that we're changing, so that's I2. And then we have this other constant here, 0.002 times N1. Again, N1 is just a constant we need to determine, and that's our B. And Y, again, this is just the resulting variable that we're going to get. So this is in the form of a straight line, so that's why we expect to see this straight line when we plot this data. So now we need to actually calculate the current in, or the number of windings, 1 and 2. So we're going to want to use our graph here for this. And so what a good thing to do is to look for points that look really easy to use. So points where they lie right on an intersection, where we can really estimate a good value for them. So the points that I'm going to use here are the first one where we have I2 is equal to 2 milliamps. So that's going to be 0.002 amps. And when we have that, this factor BL over mu naught is equal to, if we look at the value on the y-axis, that's equal to 8. And the other point that looks nice to use is going to be when I2 is equal to 5 milliamps, then our BL over mu naught is equal to 16, because those both lie close to a little corner or intersection of the grid. So it looks like it's easy to estimate. So I'm going to pick those 2 points to use. Theory, it doesn't really matter which points but the ones that are in the middle of the lines are a little bit harder to estimate the exact value, so you may not get a great number when you use those. So now what we want to do, we know that we're going to need 2 points because we have 2 unknown values here. We don't know n1 and we don't know n2. So that tells us that we're going to need 2 points. And now let's set up an equation using both of these points that we have. So the first one, we're going to get 8 because that's our value on the left side. We have our 0.002 times n1. And then our I2 here is 0.002 again, and that's times n2. So that's our first expression. And then the second one, the same thing, but now we have 0.005 and 16 that we're plugging in. So now we have to solve these equations. This is a system of equations with 2 unknowns. And there are a few different ways to solve a system of equations. One would be substitution, but I'm going to use the method of subtraction, where we subtract an entire equation from the other, because we have the same term, 0.002 and 1, in both of these equations. So what I'm going to do, I'm just going to flip the order of this here. I'm going to subtract the second equation from the first equation. So I'm going to add a minus sign down here. And when we kind of sum this all up, what we're going to get is 8. These terms are going to cancel out, this 0.002 times n1. We're going to get 8, and then we have 0.005 minus 0.002 times n2. So that's just 8 equals 0.003 times n2. And when we solve for that, that's going to give us n2 is 2,667. I'm rounding up because it doesn't really make sense to say that there's a fractional number of turns. So I'm just going to say that this is 2667 here, so that we don't have to deal with fractional numbers of number of windings. So now we have n2. So now all we have to do is pick one of our equations. Let's say this one, just because, and plug in n2 here and just solve for n1. And what that's going to give us is n1 equals 1333. Again, I'm rounding to the nearest winding so that we don't have fractional numbers of windings. So this is going to be the answer to part B here. We've figured out n1 and n2. Now part C asks if the current in winding 1 remains the same, but now winding in the second current is now going in the other direction, what is the magnetic field going to be? So let's take our equation, original equation up here. This is the one with everything totally general. We're going to have this. I'll just put this over here. We have our n1 and n2, so I'm just going to plug that in so that we just have everything explicit here. n1, n2, 2667. We know our L. I'm going to plug that in now because we're asking to find just the magnetic field. We don't need this. We don't want this whole L over mu naught. So this we can plug in right away as 0.4. So we're now told, we're trying to find B, and we're told that I2 is now 5 milliamps, so 0.005, but in the opposite direction. So what we can do when we have a current in the opposite direction, we can just flip its sign. So instead of plugging in just positive 0.005 here, I'm going to make it negative. So if we just plug this in as a negative number, that takes into account the fact that this is in a different direction than this. So now we have all of our, everything here is in terms of a number that we know. So we want to just, if we just want to solve for B, all we have to do is just move this factor of mu naught over to this side. So we have this here, and over here. And we want to divide by this factor of 0.4 at the very end. So this is what we're going to plug in and solve for. And when we do that, we should get B is equal to minus 3.4 times 10 to the minus 5 Tesla. And this minus sign here again indicates that the field is now in the opposite direction as it was before, because before we had only positive values for B, So we don't know what direction that original B is, but this minus sign now tells us that it's going to be in the opposite direction as it was before. But this magnitude is going to be 3.4 times 10 to the minus 5 Tesla.